Hello, everyone. My name is Festus Hategekimana. I do SSD security architecture development work at Solidime. And for the past few years, I've been involved within TCG Storage Workgroup Organization to help with the development and in the standardization of key prior technology. For folks who are not familiar, key prior is our next generation data at rest protection architecture for self-encrypting drive. It is a technology that is being co-developed by NVMe and TCG. So today, I'm here on behalf of TCG Storage Workgroup Organization to provide you with a quick update on KeepIO specification development work and what you can expect from these specs once they become public in upcoming weeks. I do recognize, however, that not everyone is familiar with what KeepIO is, so we're going to spend a few minutes talking about, what KeepIO is, what KeepIO is not. We'll talk about how KeepIO differs from existing self-encrypting and draft technology. So the agenda of our talk today is we'll start with a quick overview of existing self-encrypting draft systems, how they implemented, the benefits and challenges of these systems. And then we'll jump into, how KeepIO solve those challenges and retain the benefits of existing systems. We'll look at KeepIO architecture, its own, set of benefits and some of the challenges that it uniquely presents. And then we'll look at how you can leverage KeepIO in your storage applications. We'll close with a quick overview of specification status across different standard bodies that are working on KeepIO. Okay, let me grab a pointer to help us through the presentation. Okay, so existing self-encrypting draft technologies, the way they implement it today, you have a hardware encryption engine, right? That is native, that reside within a CD drive, and this encryption engine is used to encrypt user data as it come into the drive, or decrypt as coming out of the drive, right? The encryption keys that this engine uses, they're called media encryption keys, and these media encryption keys are generated by the drives themselves, and they're stored inside the drive. They also associated, the media encryption keys are associated with what I will call a range of host sectors, or ALBAs. So each range will have its own unique key, right? One of the requirements is that, the range has to be composed of a contiguous set of host sectors. So if you need to use, for instance, as a particular key to encrypt a file, but the file spans across multiple ranges, you won't be able to do that, right? You only limit it to whatever the boundary of the range is. So TCG and other standards body, they've developed data rest protection based on top of this native hardware encryption technology. Well, basically, as you can see, the security intuition is to tie the protection of the host data to the protection of the media encryption keys, right? Because if you're unable to have access to media encryption keys, then you would not be able to decrypt. You'll not be able to decrypt the host data that is stored in non-faulted media. So the way the protection of this media encryption key work is you effectively tie the media encryption keys to a credential that is only known to an external, host entity. And let's call that credential a PIN, or some authentication key. The current implementation at a high level, they run that authentication key or a PIN through some key derivation function to derive a symmetric key that is then used to protect the media encryption key. What that does, it allows these SCD draft to maintain the protection of media encryption key without having access, obviously, to the authentication, without having a persistent access to that authentication key or PIN. The Some of the obvious benefits of this is you have obviously inline hardware encryption native to the storage drive. So the host offload that encryption compute to the drive, and thereby increasing the general performance of the system. You also have flexible access control to media encryption to host data, right? Depending on how you choose, to manage the access to the authentication credential. And then obviously you have data risk protection, especially following a file loss or when the host, decided to stop authenticating to the drive, since the drive does not natively, doesn't have access to the PIN, to the authentication PIN, then effectively has no access to plain text mirror encryption key. So there's no way to decrypt the data that is stored on non-volatile media. The challenge, though, the challenge of this type of system is then, because keys are tightly coupled to where the data reside, you are unable to encrypt, to encrypt storage objects that may sit at abstraction layers that are higher than individual volumes or individual range, or that are higher than individual range or higher than a single individual storage drive, right? So that effectively, takes away the, for folks familiar with software encryption, it takes away that type of flexibility of having able to, encrypt a file and distribute a storage abstraction that, higher than a single drive. The other challenge of this type of architecture is the keys, because the keys are held internally on the drive, you always have a risk of potentially poor implementations that may risk the confidentiality of user data if those keys were to leak, either via physical tampering or other means. There's also the concern that this type of implementation, they don't scale well as if the drive capacity continue to increase and the drives are being shared in cloud environments, where when you have multiple tenants accessing various resources on non-volatile media. So within Storage Workgroup, we've been trying to see how, especially, how we can solve these two problems, but also maintain the benefits that that current system provide today. This is where Key Prior comes in, and effectively what Key Prior does is it offload the key management. It basically, it allows all the key management to take place external to the drive. And what that means is, it allows potentially, use case where you may have some, key manager. The key manager could be implemented, as an external key management server, or as a part of a key management service within a, virtual machine monitor, for example. And say, this key manager has a way to acquire these keys that control data for particular applications. So KeyPrior allows the host to be able to relay the keys that are tied to those applications inside the storage drive key cache. The interface to relay the key, to inject the keys into the drive, is the standard NVMe security send receive, but Key Prior defines, an interface to use KME protocol for key formatting, purpose. So we do use, you can think of it as basically protocol stack level. You have your NVMe security send receive, you have your TCG protocol, and then underneath you have your KME payload that basically structure the actual key you're sending down into the drive, and a set of attribute that defines what namespace is the key intended to, and which index within the hardware key cache the key should be mapped to, and that index is referred to as key tag. The confidentiality of the media encryption key obviously is paramount to us. So those keys are encrypted using key encryption keys that are also held by the host entities that owns the media encryption keys. So once the keys have been inserted into the hardware key cache, then the storage device is ready to start then using those keys, those individual keys that are mapped to individual application, is ready to start using them to perform read and write operations. So in this example, you have application one, application two, they can issue their commands. Your storage front end layer on host side obviously would need to be able to map um, those applications to the right namespaces within the storage drive, and then it needs to be able to specify within the write or read command the key tag or the index within the key cache that map to the key that is being used by the application. As you can see, this gives better control to the host to decide where on storage or non-volatile media the key the data can reside. And you can see now, since you have better control on the keys, you can effectively encrypt an object or the file and distribute across ranges. They don't have to be contiguous, right? It could be anywhere within a drive. But also this means that effectively, you can use the same key, the same key for this application to encrypt data and distribute across not just a single drive, but across multiple drive. One important thing to note here is that key prior drive, they do not store persistently the media encryption keys. So on power loss, or if the host issue a command to purge the key cache, those keys are lost. And obviously, the data remains, but the drive has no access to the key. So that presents actually some really nice properties. Number one, you get obviously, you know, since the host owns and controls media encryption keys and injection, that means you can have better guarantees on the key management implementation, since all the life cycle of the key is implemented by the host and maintained by the host. You can have the key properly stored in it, some type of hardware secure modules. You can have auditable policies around how keys are managed. So that's really a nice benefits for enterprise solutions where they need tighter and better control of the media encryption keys that are used to protect their data. The other benefit is it's flexible, right? You get the software flexibility as the host can associate a single key with a data object that spans across not just a single drive, but multiple drive. And that means you can also erase at that granularity, right? Not just a single drive, but you can erase across a distributed storage system by just purging the key on your end and just issuing a simple command to clear the index within the key cache, that is utilizing the key. You still have flexible access control, that you get with existing systems. This time it's only enforced via key wrapping. The entity key wrapping of the media encryption keys, right? The entity that owns this key encryption key that's used to wrap the media encryption keys obviously will have access to that media encryption key. So policies around key management can provide nice way to configure who has access to media encryption key and effectively to the host data. The key encryption key themselves, when they're injected, they're also protected. There are various protection schemes that key prior specification define. But the fact that the storage device has no persistent knowledge of media encryption keys, that means you effectively get stronger data rest protection guarantees, even in event where there's a physical loss of the drive. The commission process become easier since the drive has no knowledge of the keys. So anyone with access to drive, there's nothing for them to gain since all the keys are only known to an external host entity. You get better, media encryption key scaling is, a drive is shared among multiple tenants. The only limit to the number of users really can have is whatever the key management service support. You have some type of a limit, a runtime of the number of keys you can use at the same time that could be active at the same time, and that limit is imposed by the size of your hardware key cache. But the actual upper bound on the total number you could have is whatever the key management system support. Because even if the size of the hardware key cache may be limited, you can always swap in and out the keys you want. There should not be, there's no expectation on any performance drop. In event you have to swap out keys in and out. Effectively, any type of performance degradation is just comparable to existing SED system where you have to unlock, right, supply a PIN to be able to get plain text media encryption keys into the hardware key cache and then process IO. So there's nothing, there's no expectation of a performance drop in the event you support even more users than what the capacity of the hardware key cache allow. One of the key challenges, key prior is we think this was also important. It's important to call out is because the host owns all the keys. That means the host need to be able to track how keys, how applications, the keys, the application to key mapping to ensure that the right keys are being used for the correct application. In event, wrong keys are used, if, for example, you try to read it with a wrong key, you would not be able to get the data, right? You're going to end up with type of error, and the host needs to be able to know what to do in those type of situations. So we think that's not an insignificant management task, especially if you need to, if you have hundreds of thousands applications running, and you have individual key for those applications that need to be managed. A few example use case, how can you leverage key priority in your application? There are a couple key ownership models that current key priority architecture allows. One of the easier one is, key ownership models where the host or the tenants within VMs have direct control of the media encryption keys. So key priority allows to set up secure transport of media encryption keys from the tenants, the end tenants, from all the way to end tenants to the storage drive where the key is going to be used. It doesn't matter the type of storage topologies that exist between the end user and the SSD. You could have, SSD sitting behind fabrics or direct attached systems. It doesn't matter. All those layers in between, all they see is an encrypted payload of the key and no access to plaintext key. The only entity that will see the key is the owner and the hardware key cache. In this model, owner controls the ability to inject the key, delete the key, updating the key, and obviously the ability to erase data is simpler because data isn't tied to a particular location, right? As long as the host purge the key on a end, or the tenant purge the key on a end, and they clear, the issue a command to clear the key cache where the keys are being used, you can effectively achieve crypto erase, ensure that there's no confidentiality risk on the data. The other use case is obviously key delegation. Some tenants, host users that may not, want to own and manage their own keys, so they may delegate that to storage infrastructure or platform owners, and that's fine. And key prior support that type of models as well. Well, the key exchange happen between the SSD, NVMe controller or whatever layer of storage infrastructure that will be managing the key. In that case, the storage infrastructure that's managing the key will own the lifecycle of the key, including injecting the key, updating the key, or deleting the key, right? Same principle on data erasure remains the same. The drive has no persistent knowledge of these keys, so a simple, clear key cache and getting rid of the key ensure that that data remains inaccessible to anyone who can have physical possession or can even reinsert the key or reinsert uh, the drive into their own host systems. To get us to conclusion, the key area it's been fairly in development for a couple years now, and I think some of the specifications have already matured and have been public. Yeah, but from a system view, I want to show which components of the specifications which component the systems are in the scope and which standards body own those components and the status of the specification for behavior for those components. Host entity interactions. So anything, the host does around it, occurring keys for the applications, whether the key management is being implemented by the storage infrastructure itself or the users themselves. We don't concern ourselves with those interactions, so those are not in scope within TCG or NVMe. But interface interactions, right, to inject the keys into the drive, to specify which key tag the particular application needs to use in write and read commands. All those interface applications, interactions that are in scope for us in TCG and NVMe. So for NVMe, the spec of interest is the NVMe TP4055. That one has already been integrated. It's public. It does specify how does the whole, way the host discover key pair capability supported by the drive, but also how the commands have been extended to support key pair. TCG storage interface interaction specification, CIS, version 111. It's recently became public. That one is a TCG specification that basically maps TCG error states to NVMe, and it explains what the host can expect in the event receives a key pair error, whether you have garbage data or partial data or node data. All of those scenarios are covered in TCG specs. There is the core TCG key pair spec, the subsystem class specification that is soon to be in a public review. And that one defines the interface for key injection, the protection of the keys as they're being transported into the storage device, the set of KME protocol elements that are being using for key formatting and key transport, and then the actual processing rules that key pair drives implement. We think it's important that system implementers are aware of not only the expectation at an interface, but also how drives are processing requests, the way request needs to be formatted and the way the drive expect the request to be formatted and how we process them. And finally, there is an app note, the TCG key pair SoC application note that I've been working on. The app note covers anything from host discovery of key pair capabilities, but also how to inject the key, how to inject the key encryption keys, min encryption keys, how to tie them to a particular namespace, or how to specify various key index and hardware key cache and how to map all those to a particular keys. That one it's recently passed our internal review, so it's soon also be in a public review, and we're really hoping, that folks will take advantage of that as they're starting to play with Keep.io in your proof of concept or other production, even in the production implementations. So to close, Keep.io, it provides, it's a great data rest protection technology, provides flexible control of encryption, where you can associate, you can encrypt at any granular level, higher or lower than individual or driver volume, and still with the performance of a storage device, hardware encryption. You get obviously stronger confidentiality guarantees with data at rest, since the drive has no persistent access to the encryption keys. The only access it has is the keys and runtimes that are being used to process I/O. It is Keep.io, it is an industry standard-based design, so you could expect multi-vendor interop anywhere Keep.io is supported. And lastly, it is a TCG standard, so we've made sure that existing TCG software stack is very compatible with Keep.io to minimize the amount of development effort that our system will need to implement to support Keep.io. So please come join us in TCG Search Work Group um, to continue discussion on Keep.io, but also, review all these documents that are coming out. Let us know what you think. Additional use case that you think we could support, but also if areas that you think we can provide more flexibility to host applications that where data rest protection is needed, especially in multi-tenancy situation. Thank you.